If life ever existed on Mars, it wouldn't be a philosophical idea. It would be a fact that rewrites biology, evolution, and the meaning of rare. And here's the uncomfortable truth. Mars is not just a dead red desert. Mars is a crime scene. It has clues everywhere: river valleys, lake beds, minerals that only form in water, methane spikes that appear and vanish, and rocks that look like they were altered by chemistry that had no business happening on a dry, frozen world. So tonight, we're going to ask one question with brutal honesty. Is life on Mars possible, right now or in the past? And what is the strongest evidence we actually have? Not rumors, not memes, evidence. And by the end, you'll see the real reason scientists keep going back to Mars. Because it's the closest place in the solar system where life could have started, survived, or left fingerprints we can still read. Let's start with the big misunderstanding. When people ask, is there life on Mars? They usually imagine animals, plants, or at least microbes crawling around on the surface. But the surface of Mars is one of the most hostile environments we know. It's cold, often far below freezing. The atmosphere is thin, about 1% of Earth's pressure, so liquid water boils or sublimates quickly. There's intense radiation because Mars has no global magnetic field like Earth, and only a thin atmosphere to block cosmic rays and solar particles. And the soil contains reactive chemicals, including perchlorates, that can be harsh to organic molecules. If you dropped a bacterium from Earth onto the open Martian surface, it would be cooked by radiation, dehydrated, and chemically attacked. The surface is basically a sterilizer. So, if life exists today, it almost certainly hides underground, where soil and rock can shield it from radiation and stabilize temperatures. Now, the second misunderstanding. People think Mars was always like this. It wasn't. Mars today is cold and dry. But Mars in the deep past was different. Early Mars had more atmosphere, more warmth, and, this is the key, liquid water on the surface. Not just occasional trickles, but rivers and lakes, and possibly even an ocean. How do we know that? Because we can see the shapes water carves. Mars has valley networks that look like dried river systems. It has deltas, fan-shaped deposits where rivers empty into standing water. It has shore-like terraces and basin structures consistent with ancient lakes. And it has vast outflow channels, enormous scars that look like catastrophic floods. But geology can be deceptive. So the stronger evidence is chemical. Rovers and orbiters have found minerals like clays that typically form when rock interacts with water for long periods. They've found sulfates that can form as water evaporates and concentrates salts. They've found carbonates in some regions, which are another sign of water interacting with atmosphere and rock. This is not a single clue. It's a pattern that covers the planet. Mars was once wet. And wherever you have stable liquid water, chemistry becomes creative. On Earth, life appears very early in the geological record. That doesn't prove life is easy, but it proves life can appear quickly once conditions are right. So Mars had a window, maybe hundreds of millions of years, maybe longer, where the ingredients and environment could have allowed life to start. What ingredients? Life as we know it needs a few basics: liquid water, an energy source, and building blocks like carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur. Mars had those. Meteorites and early planetary formation deliver organic compounds. Volcanoes and hydrothermal systems deliver energy gradients. Water provides the solvent. So, possible is not a crazy claim. It's chemically reasonable. Now we go from possibility to evidence, and we have to be disciplined. The strongest evidence we have is not "we found life." It's "we found environments that could have supported life and preserved its traces." Mars is full of ancient lake beds. One of the most famous is in Jezero crater, where a river delta once fed a lake. Deltas are special because they trap sediments. On Earth, sediments can preserve microfossils and chemical biosignatures for billions of years. If Mars ever had microbes in that lake, the delta is one of the best places to catch their fingerprints. That's why rovers go to places that look boring in photos: layered rocks, clays, deltas, dried mudstones. Those are the pages where history is written. Now, let's address the evidence people love because it feels like a smoking gun: methane. Methane is a simple molecule, 1 carbon, 4 hydrogens. On Earth, a huge fraction of methane in the atmosphere is produced by biology, microbes in swamps, guts, and seafloors. But methane can also be produced without life through geology. For example, water rock reactions like serpentinization can generate hydrogen, which can then help produce methane. Impacts and certain chemical processes can also contribute. So methane alone doesn't prove life. But on Mars, methane is weird, because it appears in spikes and then disappears. Methane in an atmosphere should persist for a while because it's broken down by sunlight and chemistry over years. If Mars has short-lived methane plumes, it suggests either the methane is being produced in bursts or it is being destroyed faster than expected, or both. That's a mystery worth chasing. If methane is coming from underground, it could come from geologic processes, or it could come from microbes. The only way to tell is to measure the methane's isotopes and accompanying gases, and to understand where and when it appears. Methane on Mars is like a faint smell in a locked room. It doesn't tell you who is inside, but it tells you something is happening. Now we have to talk about the most infamous "maybe we found life" moment in Mars history: the Viking landers in the 1970s. Viking carried experiments designed to detect microbial metabolism in Martian soil. One of the experiments, called the labeled release experiment, gave an intriguing result. When nutrients were added to the soil, gases were released in a way that looked like metabolism. For a moment, it looked like life. But other instruments detected no organic molecules in the soil, which seemed to contradict biology. Over time, the mainstream interpretation became that Viking saw a chemical reaction in the soil, not life. And then decades later, we discovered something that reopened the story. Perchlorates. Perchlorates are reactive salts that can destroy organic molecules when heated during analysis. Viking's organic detection method involved heating the soil. If perchlorates were present, they could have destroyed organics before they could be detected, producing false negatives. So Viking might have seen chemistry, or it might have seen biology masked by chemistry. The data are still debated. That's not a conspiracy. It's the reality of ambiguous evidence in a hostile environment. The lesson is simple. Mars does not give easy answers. Now, let's talk about the kind of evidence that would be hard to explain without life: biosignatures. A biosignature can be a shape, like microfossils, but shapes can fool you. A biosignature can be a chemical pattern, certain ratios of carbon isotopes, specific organic molecules, or complex structures like lipids. But chemistry can produce some organic molecules without life, especially over long times. The strongest evidence usually comes from multiple lines that agree. A habitable environment, plus organics, plus a chemical pattern that suggests biology, plus a context that makes non-biological explanations unlikely. Mars rovers have found organic molecules in ancient rocks. That doesn't mean life. Organic molecules can be delivered by meteorites or made by chemistry. But organics in the right setting, ancient lake sediments, clays that protect molecules, are promising. We've also found signs of past hydrothermal activity. Hydrothermal systems on Earth are hotspots for life because they provide energy gradients and chemical nutrients. If early Mars had hydrothermal vents or hot springs, it could have been a cradle. And then there's ice. Mars has a lot of water ice, including at the poles and in subsurface regions at mid-latitudes. Ice is a preservative. If life ever existed and then died out, frozen ground could preserve organic remains or chemical fingerprints. Now comes the hardest part: life today. Could microbes live underground on Mars right now? Possibly. On Earth, life exists in extreme environments that once seemed impossible. Deep underground, in Antarctic ice, in acidic lakes, in hot springs, in high radiation zones. Microbes can survive on tiny amounts of energy. Some live by eating rock, using chemical reactions with minerals. Some can survive long periods dormant, waiting for brief moments of liquid water. Mars underground could provide radiation shielding, more stable temperatures, potential liquid water in briny form, chemical energy from rock-water interactions. But the key uncertainty is liquid water. Pure water is unstable on the surface. Underground, pressure increases and temperatures can rise, making liquid water more plausible. Also, salts can lower freezing points, creating brines that remain liquid at colder temperatures. This leads to one of the most controversial clues: hints of subsurface lakes beneath the polar ice. Radar data have been interpreted by some as evidence of liquid water pockets. Other scientists argue those signals could come from certain minerals or ice structures. This is still debated. But even without large lakes, thin films of brine could exist seasonally or transiently. Life doesn't need oceans. Microbes can live in microscopic pores. So the possibility remains: Mars could host a hidden biosphere. If that's true, it changes everything, because it would mean life is not a rare miracle. It is something chemistry does when it gets time and water. Now let's ask the question everyone quietly wants. If Mars had life, where did it go? Mars lost its habitability because it lost its atmosphere and much of its surface water. The leading story is that early Mars had a stronger magnetic field. That magnetic field protected its atmosphere from being stripped by the solar wind. But at some point, Mars's dynamo weakened or shut down. Without a strong global magnetic field, the solar wind could erode the upper atmosphere over long time periods. Mars's lower gravity also makes it easier for gases to escape. As atmosphere thinned, pressure dropped. Water became less stable. The planet cooled. Surface lakes froze or evaporated. The world became the desert we see. Life, if it existed, had three options: adapt underground, go dormant, die out. On Earth, microbes can survive extreme change by retreating to protected niches. Mars might have done the same. Or Mars might have crossed a threshold too harsh to survive. But even if life died, it could have left traces: fossils, organics, isotopic patterns locked in ancient rocks. And that's why returning samples from Mars is such a big deal. The most powerful instruments aren't on rovers. They're in Earth laboratories. If you can bring ancient Martian rocks back and analyze them with the full arsenal of modern chemistry, you can test for subtle biosignatures far beyond what a rover can do. Now, there's a reason this question is emotionally charged: contamination. If Mars has life today, we must avoid killing it or confusing it with Earth life. And if we bring samples back, we must avoid bringing a dangerous organism to Earth. Most scientists consider the risk of a Martian pathogen extremely low because Mars is harsh and a Martian microbe would not be adapted to infect Earth life. But caution is not optional. Planetary protection exists because the stakes are real. You can destroy the very evidence you went to look for. Now, let's do a thought experiment that makes the evidence clearer. Imagine you find a dried lake bed on Earth from 3.5 billion years ago. You drill into its sediment layers. You find clays that preserve organics. You find simple organic molecules. You find a carbon isotope ratio that is strongly biased toward the lighter isotope, a known signature of biological processing. You find microscopic structures consistent with cells, and you find these signatures repeating across multiple layers. Would you say life existed here? Yes. Now imagine the same pattern on Mars. That would be one of the biggest discoveries in human history. So what's stopping us? Access and ambiguity. Mars is far. Rovers are limited. The most convincing evidence requires high-precision lab work and careful context. And Mars loves to mimic life with chemistry. Many non-biological processes can create organics and structures. That's why we need multiple lines. So where are we right now? Right now, the honest answer is we do not have proof of life on Mars. But we have something more interesting than a yes or no. We have a planet that was once habitable, that still has water ice, that has organics, and that keeps throwing signals, like methane, that suggest active chemistry. Mars remains the best nearby place to answer one of the deepest questions humans can ask. Is life a cosmic accident or a cosmic habit? Now, let's make the viral part of this story land, because it's what makes people keep watching. If Mars had life, even microbial, three massive ideas change instantly. First, the origin of life. If life started independently on Mars and on Earth, then life is likely common wherever conditions allow. That means the universe could be full of biospheres. Second, the definition of life. If Martian life has a different biochemistry, different amino acids, different genetic molecules, or a different cellular architecture, then life is broader than we thought. It would mean chemistry can build living systems in multiple ways. Third, our future. If Mars is sterile, it becomes a blank canvas for human colonization in a very different ethical sense. If Mars has life, Mars becomes a protected ecosystem we must treat with extreme care. The decision of whether to terraform Mars stops being engineering and becomes moral philosophy. So the question, is life on Mars possible, is not just about microbes. It's about what kind of universe we live in and what kind of species we are. Now, let's address the strongest counter-argument. Mars is dead. It's been dead too long. It's true that Mars has been harsh for billions of years, but life on Earth survived mass extinctions, snowball Earth phases, global volcanic winters, and deep-time climate swings. Microbes are unbelievably resilient. Some survive in salt crystals for millions of years. Some survive in dormant states and reactivate when conditions improve. Some survive in deep rock for geological times. So too long doesn't automatically mean impossible. It means hard to find. And that may be the real reason we haven't found it yet. Not because it's absent, but because it's hidden. If life exists underground, it won't send smoke signals. It won't paint the surface green. It will be sparse, slow, and quiet, living in cracks with minimal energy. To find that, you need to drill. You need to go deeper than rovers usually can. You need to target the right sites, places with past water, present ice, and chemical energy. And you need patience. Now, let's close with a final image that makes Mars feel less like a dead dot and more like a question. Picture early Mars with rivers flowing into a crater lake. The sky is thicker. The climate is colder than Earth's, but stable enough for water to persist. Sediments settle at the bottom, layer by layer. Minerals form that lock in chemistry. If microbes exist, they live at the water's edge, in the mud, in the mineral pores, feeding on chemical gradients, reproducing, dying, leaving molecules and isotopic fingerprints behind. Then the planet changes. Atmosphere thins. Water retreats. The lake freezes, then vanishes. Dust covers the layers. Radiation sterilizes the surface, but below, the sediment remains sealed and cold, like a vault. That vault may be sitting there right now, holding the oldest biological record we could ever read from another world. And this is why the search is so addictive. Because Mars is close enough to touch with robots, yet alien enough to tell us whether life is a once-in-the-universe fluke or a rule. So is life on Mars possible? Yes. It was possible in the past. It may still be possible underground today. And the evidence we have is not a verdict, but a trail of clues leading us toward the most important discovery we could make in our lifetime. The only way to finish the story is to keep digging, literally, into the red planet's ancient, silent pages. And if one day we find a single unmistakable biosignature in those pages, you will never hear the word Mars the same way again.